Hi everyone, my name is Ivan, and my colleague David and I will be talking today about how cost constraint influence service architecture. A year ago, my colleague Andre and I were here. We were presenting scaling challenges for our feature store from 1 million to 1 billion features per second. We presented a few tricks and some some decisions that led us to reach this number of 1 billion features per second, and we were happy with the result. Until our leadership came and said that we need to make our system almost 10 times cheaper. And we were like, what? What are you talking about? Are you crazy? We just had this talk on P99 CONF, and if you watch it, you may realize that the services are actually pretty cheap. But they say, yeah, good talk, but we still need to make it cheaper. And so we started thinking. And while thinking, we realized that cloud builds are a big mess. Like, for instance, both AWS and GCP, they have around 40,000 different SKUs. It's pretty hard to figure out what they charge for what. And it's also easy to lose track on different components. For instance, you can launch some VM, forget about it, but be charged for it forever. And cloud providers don't make it easier to make such discoveries, of course. They're not incentivized to do. And so the first thing that we did was the ruthless inventory or attribution. We wanted to understand exactly for each line of the cloud bill where it came from. And we also wanted to make it continuous. So not only like we have this attribution like once a month, for instance. We wanted to do it every day. And while doing so, we realized in the cost-saving project, there is this funnel. And on top of the funnel, it's actually boring stuff, like figuring out what is running for what, killing some unused instances, killing some unused S3 buckets, and so on and so forth. It might not be like compelling thing to do, but it actually can lead to pretty cool results. In our case, it led to nice cost saving just doing so. It was just not enough, and so we moved to the second item in this funnel called cloud traps. The first trap that we ran into was Kubernetes wastage. Kubernetes is a cool and versatile system, and it's pretty convenient to use in cloud with managed offerings. But the thing is that what we launched in Kubernetes and what we charged for are a bit different. We launched so-called pods, basically containers, but pods get scheduled to nodes, which is basically VM, and we actually charged for nodes, for virtual machines. And so when we plan launching some service on Kubernetes, we must ensure that size of the pods that will be scheduled are well aligned with the size of the nodes. Otherwise, there will be a wastage. But what happens if we want to run multiple different services with different specs? It will inevitably lead to the wastage because Kubernetes scheduler will schedule these pods on nodes, and at some point we will run into a situation then there is not enough either CPU or memory, and so basically we have some wastage and cannot schedule anything. And okay, we may decide, fine, we don't want this heterogeneous approach. It's too complex. It leads to wastage. So let's have a homogeneous approach. Let's have a node pool per service. But then we quickly realized that it's not a panacea, unfortunately. We will still have wastage because we will run into a situation when some nodes are under-provisioned, underutilized. And so the solution for this is to dynamically allocate nodes based on the actual workloads that are running. There are some services that do this in open source space. There is a system called Carpenter. In cloud, for instance, in GCP, there is GKey Autopilot, and as far as I know, Azure soon will launch the similar service. And there are commercial systems that run on any cloud. We use CastAI, And in addition to do this optimization, it also does some pretty nice stuff, like it may try to utilize commitment in full. It may try to first launch spot nodes and so on and so forth. The second trap, which we call cloud tax, is about cross availability zone network egress cost. When we run system in the cloud, we obviously want some resilience, and so we want to launch it in multiple availability zones. But the traffic between these zones may be charged for, and so like assume this example when we run a Scilla database, and we want to have replication factor 3, and we want to have 3 racks in Scilla. 3 racks in Scilla means that Scilla will allocate data according to these racks. So basically, for replication factor 3, it will copy data inside each rack. And so like it's natural to map each rack to availability zone. But what happens if we want to read from this cluster and assume that we picked the driver without any additional settings, just took some vanilla driver and just try to read. The traffic can cross the zone twice. First, it can cross the zone when reaching a particular node when we make a call, but this node may not have the data. So this node must make a call again, and this call again can cross the zones. And so like there is a simple math, and if we have a traffic T, the math tells us that we will be charged for this traffic T in terms of nice. What we can do about this? The first thing we can do is to use token-aware routing. Token-aware routing is important for performance, but also it's important for cost, because client will pick the node that definitely has the data, and so the Scilla will not need to make the second hop, and so like we will reduce our charge from T to 2/3 T. And the second thing that we can do, in addition to token-aware routing, we may want to have zone-aware routing. In this case, we will pick not only node that has the data, but also the node that inside our zone. And so in this case, we make a read, but the traffic never cross the zone, and we will be charged 0. What about writes? Assume we learned everything from the previous slides about reads, and so like we picked the driver with zone-aware routing, with token-aware routing, but still, write means that Scilla needs to replicate the data, and what it means it means that the coordinator needs to copy data to 2 additional nodes. So for the traffic of size T, we will be charged 2T nice. Can we do something about it? And here comes the trade-offs that may be influenced by cost. In our case, we realized there are certain cases when we don't need that high catastrophic resiliency. Basically, we don't need to run neither service nor Scilla in 3 availability zone. It's fine to run. Yes, we lose we lose the resiliency for the case when both zones dies, but it's a nice trade-off in this case. But in terms of the cost, what does it mean if we run Scilla in 2 zones instead of 3? It means that for the traffic of size T, for writes, we will be charged 1.5 T instead of 2 T. And moreover, we actually can do more. In Scilla, there is a concept of data centers. And what's interesting about data centers is that Scilla makes sure that when it replicates data between 2 data centers, the traffic cross data centers only once. In terms of the zone, it means that the traffic will cross zone only once. So instead of single data center with replication factor 3, we can have 2 data centers, and each of them have the replication factor 2. But in terms of the nice, we will be charged for traffic T, we will be charged only T. It seems that it's the lowest charge we can have for the case when cloud provider charges for nice. But we can actually do in some unconventional route, and we can research and realize that not all cloud providers charge for nice. some providers like Azure or Oracle Cloud, they don't charge. And so in this case, we don't need to do all these complex things like 2 data center setup or 2 nodes, 2 zones setups. We can have as many availability zones as we want and have zero nice costs. That was all that I wanted to present in terms of cloud traps. Obviously, there are more of them, just not enough time to present all of them. And I want to hand over microphone to David, who will be talking about more interesting stuff for software engineers, namely compute optimization. David, microphone to you.
Thanks a lot, Ivan. Now, I'd like to tell you about some of the optimizations we've done to our feature store. So let's have a quick look at the architecture first. Firstly, the responsibility of the feature store is to compute, store, and serve features for our recommendation system. It naturally divides into these 3 components. The compute is a number of Flink jobs which ingest event streams, process them to compute features, and sync them to our storage layer. The storage layer is a ScyllaDB cluster, and the serving layer is a distributed gRPC service responsible for caching and handling consumer requests. I won't talk about the compute part today, but if you're interested, Ivan actually did a talk at KubeCon earlier this year, and the slides are linked here. So let's talk about the store first. The first thing I'd like to mention is scalability. People tend to think that databases are not scalable, whereas the reality is they're not very elastic. I've seen databases being well over provisioned to manage tests, backfillings, or even holiday traffic months ahead. Distributed databases like Scylla are actually fairly scalable. Big kudos to Scylla support. We scale our clusters up and down many times in the year to respond to seasonal variations in traffic, for example, and that really helps us manage our costs. The key here is to always keep a buffer for unexpected events and scale in advance for known events. Although we don't use it in production yet, a special mention to tablets in Scylla v6, as this is a really solid step towards increasing elasticity. The second thing I would like to talk about is workloads. A very common problem is workloads impacting each other, the most common being writes impacting reads. This is an example of where we were in the early days of our feature store. You can see we had a nice baseline for read latency, but then we would start a backfilling job and latency would spike for some time, breaking our SLA until the backfilling's done. The common reaction to this, as I mentioned earlier, is to scale up. This is the easy and costly solution, not to mention that scaling up is not always a silver bullet. Another very common solution is to have a dual data center setup, one cluster for writes and one cluster for reads. This is a pretty nice solution, but comes with double infrastructure to manage, and that often leads to underutilized resources. Obviously, we can't have it all. It's about trade-offs. Ideally, if we could manage the share of compute allocated to different workloads, we could tune our database to fit our requirements. And that's exactly what Scylla's workload prioritization offers. Workload prioritization is a really awesome feature of Scylla. The idea is pretty simple. Different workloads can have different service levels or share of compute and will be served accordingly. This is particularly great when you have consistent workloads, and this tends to be the case for reads and writes. Under the hood, this relies on the thread per core architecture used by Scylla. Each core can be seen as a task processor, and though it's a single thread, it's async nonetheless. Tasks are queued and picked up by the async scheduler, but in reality, there are multiple queues with different priorities, and these priorities are exactly what workload prioritization is about. This is a snapshot from the setup in our cluster. As you can see, it's very basic. We have a very high share of compute given to serving, as we have strong SLAs on the read pass, which is user-facing. And most of the rest goes to feature, with a tiny share being kept for manual queries. This allows us to have very stable latencies at different levels for our jobs and our service. So moving on to the service. As I mentioned earlier, it's a large distributed gRPC service. I did put a note here that network costs can be a large chunk of costs, but mostly the majority of the cost is compute for us. Do keep an eye on egress costs. We've done a lot of work to reduce our interzone egress cost, and that can really bite you. So network costs put aside, for compute-heavy services, once you're past autoscaling, it's time to look into optimizing the application. The first advice here is not to go blindly. We set up continuous profiling very early on. There are multiple tools available by now, and integration is super straightforward. As you can maybe recognize from the screenshot, this is just a vanilla GCP profiler we're using here. This has helped us tremendously in our journey, and we actually unlocked more than 50% reduction in compute through various optimizations. So let's dive into one of these. Who says gRPC says protobuf. One big chunk of compute for us was proto-30. 95% of our requests are cached in the service. Our hottest path looks like this. Multiple entities are requested. We get most responses from cache, some from the database, merge them all, and respond. In other words, we deserialize, merge, and serialize again. This is super costly because ultimately the only thing we're doing is merging, and we don't care about the value of a particular feature at this stage, for example. So the big win here was the ability to do partial deserialization. So let's get into it. I'll start with a little primer on proto-encoding. A proto message is encoded as a series of key value records. If you're familiar with proto definition, the key is this field that you have to specify manually in the definition. The values encoding, on the other hand, depends on the type. Here's actually a screenshot from the proto documentation. Another important spec for us that I'll mention is that repeated fields, which can be seen as lists or vectors, are encoded as a sequence of records, and maps are implemented as repeated fields. I'll get back to this in a second. Let's check out a simple example. Here we have a simple inner message containing one integer and an outer message which contains a string name and a collection of inner messages. We can look at the encoding of a small example with protoscope and the records that are produced. Field 1 first with the name, and the repeated field 2 producing a record per item as expected. So what's the trick? The key is this. Strings and embedded messages like our inner message share the same encoding as bytes. This means that they are interchangeable from the perspective of SERDI, and deserializing bytes is just a copy. Now, remember what we looked at in the previous slides? Repeated fields are just a sequence of records. So similarly, a repeated string or repeated message can be deserialized as repeated bytes. This means that we can perform a lot of operations without deserializing individual elements. Here's what this looks like. Back to our message, on the right side, now you can see an alternate lazy version of our outer message, where we skip the deserialization of all individual elements. Any outer message proto can be deserialized as a lazy outer message. In practice, this means that in deserialized forms, you would get a list of serialized messages, which you can manipulate like any other list. You can delete elements, swap elements, or even append to lists. So let's get back to our cache. We store serialized features protos per entity in the cache, and our response is basically a collection of features protos. You can likely see where this is going. By leveraging this trick, we can form our response without deserializing the cache response, and that's the big win. So the question is, how big can this win be? I wrote a very simple benchmark to compare naive and lazy merging. You can go check it out on this GitHub repo. As you can see, we have a proto message with a repeated message and a map. This is very similar to this outer message we've seen earlier with the addition of a map. The operation is to merge two instances of this message, and by merge here, I mean concatenating the lists and the maps. The naive version will deserialize the message fully, append the fields, and reserialize. The lazy version will deserialize the fields to repeated bytes, append them, and serialize. So what's the impact? The result is that the lazy version is 6 times faster and requires a third of the allocs. This was a major win for us. This reduced compute and cost drastically on this service, but also dramatically improved tail latency. Not only did we save cost, but we also improved our product as a result. This same trick is now being used in production in many of our services and jobs internally. So, in conclusion, a lot of innovation came out of our cost savings initiatives. As I tried to represent in this quadrant, there is a very unhealthy way to look at cost savings by focusing on shortcuts impacting your product negatively. The key is to stay on the right side of this quadrant and aim for the sweet spot, save cost while improving the product. Before we part, there are many things we could not cover in this talk. We've done a lot of work on real-time windowed counters and Flink autoscaling, for example, which we couldn't share today. If you're interested in any of the topics, please feel free to reach out. Thanks a lot for watching.